Should I hit? There we go.
This one's kind of fun because we now get to basically stop making assumptions that aren't true. Well, we get to make fewer assumptions that aren't true. This is a part where your science classes are kind of like the scientific method, in that everything I'm teaching you, you're going to later learn. If you keep taking more science and more chemistry classes, you'll later learn. I hesitate to say I'm teaching you something wrong, but I'm teaching you assumptions. And we get to have fewer assumptions the further you go into science, the more you realize how complicated everything is, and we can say things like, well, this is true mostly, but there's some exceptions. So up to this point, we've been treating all of these chemical reactions like they go until your limiting reactant is all the way used up, right? That's the whole basis of most of our theoretical yield calculations, is assuming the reaction goes until you run out of something, right? Turns out that's not actually how chemical reactions work. Turns out most chemical reactions, not most, all chemical reactions, this is one of the few times where I get to use absolutes, all chemical reactions reach a point where they stop before they get all the way to 100% yield. Now, sometimes they get close enough to 100% yield that within sig figs, we can just assume that it's close enough, because we're going to have so little leftover reactants that we are able to make that assumption. But in some cases, reactions stop at like 70% yield. And we're going to learn how we can quantify that and predict based on what's called the equilibrium constant, how far a reaction will go. All right, and so
there we go. I don't know why it has those transitions. So the theoretical basis for this is the idea that every chemical reaction that happens can happen forward or backward. When we say all of those, that's the whole purpose of us learning conjugate acids versus conjugate bases, right? Was like, okay, well, but what if the reaction happened backwards? Because it turns out every reaction can happen forward and backward. Where it gets really interesting is at some point, if you have a reaction happening forward, you're going from a high energy state to a lower energy state. If that reaction happens at some point, you're going to get to the point where the reverse reaction is happening at the same rate as the forward reaction. If the reverse reaction is happening at the same rate as the forward reaction, what does it look like as far as measuring concentrations? Well, it looks like nothing's really changing, which isn't exactly true. It just means that everything is changing so often and there's no net change. So it doesn't mean that everything stops once you reach equilibrium. It's what's called a dynamic equilibrium. Right? And so a dynamic equilibrium is just the idea that you're going to get to a point where there's no net change observable. Right? I think I've mentioned this before in this class. I've used the example of if you only looked at my bank account on the 1st of every month, it's going to look like nothing changed from last month, because I'm going to have roughly the same balance in there the 1st of every month, because I'm spending about the same amount every month, and then a paycheck hits, right? And so if you're only checking once a month, it looks like nothing's changing in my bank account, but that's not really true, right? It just means really, if you average over the course of the whole month, there's been as many dollars deposited as there have been withdrawn. Right? And so that's the whole idea of the reactions happening at the same rate forward as backward. Doesn't mean everything stops, just means that there's no net change. All right. Once you get to equilibrium, the amount of each reactant and product are going to remain constant. That doesn't mean every molecule stays the same. Right? So this is an example of an equilibrium reaction. And technically, every reaction is an equilibrium reaction. Some of them, just like I mentioned before, they happen enough they're close enough to 100% yield that we just treat them like they're 100% yield. But if you have an equilibrium reaction, we actually indicate that we're going to be treating this as an equilibrium reaction with those forward and reverse arrows. So you see those sometimes written the way they are on the slide there. Sometimes you'll see them written like that. Key point that will really confuse you when you take OChem in a couple years. Do not do that. That means something very different in chemistry, especially in organic chemistry. This means resonance, which means you've got a couple different ways you can arrange your electrons and they wind up all being true at the same time. It's a whole quantum mechanical thing, Schrodinger's cat situation. Don't use that arrow to mean equilibrium. Equilibrium has to be two separate arrows. Either of these works. It doesn't matter which one you draw on top either. It doesn't, you know, if I drew it like that, those are the same thing, right? The main thing is we're saying the reaction's happening both directions. And occasionally you'll even see, well, if equilibrium favors making more products, you'll even see sometimes you'll make one of the arrows bigger. So draw something like that is to say that you're going to make, when it reaches equilibrium, you're going to have more products than reactants. But we'll get into that in a minute. I don't think that shows up in the slides or anything. But if you ever run into that, that's what it's saying. You're just making the forward reaction happens more than the reverse reaction. All right, so this is just another graph showing this. This means more when you take Gen Chem, when we start talking about rates. We're not going to do any of the numerical stuff behind rates in this class, though, because rates starts involving calculus concepts, and calculus isn't a prereq for this class. So we're just going to talk about it in the real general term. Your rate of your reaction of your forward reaction and your reverse reaction are going to change as the reaction progresses. And when those two are equal, when your two rates are equal, is when we can say we've reached equilibrium. Questions so far? Okay. Want to get into that? No. So basically, those reaction rates, if those two rates are going to be equal to each other, we can use actually the numerical definition. Again, this comes from the calculus, and I'm just using this as the derivation for where we're going here. You don't need to actually know the calculus for this. But if we say a forward reaction, the rate of the reaction is equal to some constant we're calling Kf for forward, times your concentration of the reactant. And your rate for your reverse reaction is going to be equal to a different constant, K for the reverse reaction, times your concentration of your product squared, because there's that 2 in the balance reaction. That 2 in the balance reaction means you need 2 of those molecules to run into each other for the reaction to happen. And so basically, from the stoichiometry here, and the idea that these two rates have to be equal to each other, I'm going to kill myself on this thing. Move that over here. I can't be the first person to have done that today. What we wind up seeing if we rearrange that system, if we set those two expressions equal to each other, do a little bit of algebra, we put both of the constants together, and then we put all of the concentrations together, we get this expression that says that at equilibrium, there's a constant that's equal to your concentration of your products over your concentration of reactants. And every reaction is going to have its own constant that we call KEQ. And this is going to be another place like the arrows where chemistry is going to be really pedantic. Uppercase K means an equilibrium constant. lowercase k's are what we call the rate constants. They had to do with how fast the reaction was happening. We're only going to be dealing with uppercase K. So just make sure you're being careful when you're writing this out, or you'll be confused when you take Gen Chem. Seems like a big chunk of this class is me trying to give you good chemistry habits so that when you take more chemistry, you're going to be set up to do well. Yeah. So this is kind of like with the atomic symbols, where you kind of sometimes you have to adapt your handwriting a little bit. The way that I always make sure I can tell the difference is I do all my lowercase k's in cursive. So if you see me write this, it's lowercase k. If I write it like that, it's an uppercase K. Things like that can be helpful, basically, as long as it's clear to you. And then just kind of overemphasize however you're doing that to show me. All right, so this is for one specific reaction we used as an example, right? This dinitrogen tetroxide turning into 2 nitrogen dioxide molecules. We can actually write, if we basically replace these different chemicals and coefficients with just A, B, C, and D, we can actually come up with a general form for an equilibrium constant. The key here, though, is this sentence right here. The ratio of rate constants is a constant. And that also means the ratio of products to reactants is a constant. And what is a ratio mathematically? Division, right? Like a fraction. Basically, 2 sides of a fraction. Division is actually exactly the word I was looking for. So all this equilibrium constant is a ratio of products over reactants. Right, and so the general form for any equilibrium expression is always going to be your products raised to their coefficients in the balanced reaction divided by your reactants raised to their coefficients. Right, and I almost myself forgot the first rule of equilibrium. All right, and I'm going to repeat this over and over again, so many times you can't possibly forget it. And because it's the way that my brain works, I'm going to put it as a moving quote. How many people have seen Fight Club? What's the first rule of Fight Club? What's the second rule of Fight Club? Don't talk about Fight Club. The first rule of equilibrium is products over reactants. The second rule of equilibrium is products over reactants, right? Over and over again. I'm going to ask you, what's the first rule of equilibrium? Products over reactants, right? It's always, and there is a third rule of equilibrium. We'll get there, but just to help that cement that in your head, products over reactants, always, every single time. And what I mean by that is this expression here. You take your products raised to their coefficients times your other product raised to the coefficient, and you divide by your reactants. Right? And this applies to every single chemical reaction out there. And every single chemical reaction in existence is going to have its own K value, its own equilibrium constant. Now, if K is really, really big, what does that tell us about how many products versus reactants we're going to have at equilibrium? Are we going to have more products or reactants? If K is really big, it means the top's going to be bigger than the bottom, right? And the first rule is products over reactants. Okay, so if K is really, really small, what does that tell us about these two? Which is bigger, the top or the bottom? The bottom. So if K is really, really small, that means that at equilibrium, you're going to, the way we phrase it is you're going to favor reactants. You're going to have more reactants around than products. right? So qualitatively, always just think of the first rule of equilibrium. All K is that ratio of products over reactants. So let's try writing equilibrium constant for a few of these. So this is a reaction that does happen. And it happens in both directions. 2 ozone molecules, O3, is a relatively kind of stable-ish molecule called ozone, like the ozone layer. 2 ozone molecules can react to make 3 O2 molecules, 3 oxygen molecules. What's the equilibrium expression look like for that? What's the first rule of equilibrium? Products over reactants. Good. So it's already balanced for you. If it's not balanced, the first thing you need to do is balance it, just like with all of our reactions, right? For that reaction, you just say, okay, concentration of O2 molecules to the third, because it has a coefficient of 3, over reactants, which is the ozone, with a coefficient of 2. Every single time. It doesn't matter that you don't know what K is, that you don't have a number for it. Writing the equilibrium expression is as simple as just taking the balanced reaction and doing products over reactants. Okay? How about B? What do we get for B? What goes on top? Products. And there's 2 of them, right? So it's NOCl squared. And then on the reactant side, it's going to be nitrogen monoxide squared and chlorine. You can write to the 1 if you want to, but that doesn't really change anything, right? If an exponent's not written, we can assume it's to the 1 because that's kind of the definition of exponents. Just like with our coefficients, if we don't have a coefficient written in front of the chlorine, we assume it's 1. The same way. All right, last but not least. K equals. Does it matter that you don't know what the heck that thing is? That's a big, giant polyatomic ion. We call it complex ion. Does it matter that we haven't learned complex ions yet? Not as far as writing equilibrium constant. Ag, NH3, 2 to the 1, right? Plus sign in there. Over concentration of Ag plus times concentration of NH3 squared. Now, this is all well and good as long as we don't have to do any math with it. You can see how all of a sudden having to do some math with this is going to start getting rather complicated rather quickly, right? Because we now have this algebraic expression where solving for X might get tricky. But there's a couple tricks that we're going to learn for dealing with that. Does it matter? Do the phases really matter here? Not as long as we're talking about gases and aqueous. All of these equilibrium expressions, we're talking about concentrations. Sometimes we'll be more specific. Instead of just calling it K, we'll say Kc for concentration. And that just means that all of our units are going to be in concentration units. Whether it's a gas or it's a solution, we can still find a concentration of a gas, right? We're going to spend next week we're going to focus on gases and how we can characterize gases, but concentration is always just an amount divided by a volume, right? So it doesn't really matter if we're talking about gases or aqueous, as long as we're being consistent. But that does lead to one other, the third rule of equilibrium. If we had a solid in here in one of our reactions, can the concentration of a solid change? It's a pure substance, right? So its concentration is kind of constant, isn't it? At a set temperature and pressure. If the concentration's constant and it's never going to change, is it really it's not a variable that's going to show up over here, is it? If it's a constant, we basically leave it off of the equilibrium expression. So for instance, we talked about autoionization of water the other day. We talked about 2 water molecules. If you have pure water, you don't really have pure water, right? Because you can go through an acid-base reaction, and what do we get as a product? What does this turn into if you have 1 water molecule act as an acid and 1 acts as a base? You get hydronium and hydroxide. What would the equilibrium expression for this reaction be? Well, it's still just products over reactants, right? So K is equal to concentration of hydroxide times concentration of hydronium. But if the water is a liquid, it's got a constant concentration. The concentration of water is always the same, which means it doesn't really show up in our equilibrium expression. It basically just gets combined with the other K value. So basically, anytime you've got a pure substance, a liquid or a solid, instead of writing it as a concentration, we just write it as 1, basically, because it's not changing. So that's your third rule of equilibrium. What are the first 2 rules of equilibrium? Products over reactants. The third rule of equilibrium is liquids and solids don't count. Right, so we actually already saw this. And this was part of our derivation of that 14 equals pH times POH. We started with, I didn't tell you what that capital K was, but I said there's this K value. It's a constant. It's 10 to the minus 14. And it's equal to concentration of hydroxide times concentration of hydronium. Solids and liquids. So we touched on this just in passing because I wanted to take the negative log of both sides so that we could get that pH plus POH equals 14. But this is the equilibrium expression for water. And water has a well-known dissociation constant. So this K value is an equilibrium constant, and this is the equilibrium expression. Right? And that allowed us to do some things like say, okay, well, what's the concentration? If these 2 are equal, what's the concentration? Right? We were able to solve that and do some algebra with that and actually get some measurable numbers out of it. All right, so we talked about the Haber process in World War I in gunpowder. I think, no? So this is a really classic example of an equilibrium expression or an equilibrium problem because this is a really important historical reaction. Fritz Haber was basically figured out how to take nitrogen from the atmosphere and combine it with hydrogen gas and make ammonia, which doesn't seem all that useful unless you know that ammonia and ammonium nitrate was one of the most important ingredients in making gunpowder. Still is. Up until the early 1900s, until about 1914, I want to say, The only place you could get ammonium nitrate for making gunpowder was you mined it out of the earth. And so they had these ammonium nitrate mines, and they would export ammonium nitrate from one country to another. Most of those mines were in South America in the early 1900s. When World War I broke out, most of the what are called the Central Powers, they weren't the Axis powers in World War I, they called them the Central Powers. They were landlocked for the most part. The Allies, the Western Allies, had better control of the oceans. And so they basically just said, okay, we're just going to blockade Germany and Turkey, or not Turkey, Ottoman Empire at the time, and Austro-Hungary. We're going to just blockade them so they can't get their ammonium nitrate. They're going to run out of gunpowder for their bullets and their bombs, and then the war will be over really quickly.
Isn't ammonia fertilizer? So
it is.
So he's like helped save lives, but also kill his country.
Exactly. It's a really good example of technology is not inherently good or bad. I'm going to start with the World War I piece, because basically what allowed World War I to drag on forever was the fact that Fritz Haber was German and developed a way to make ammonia in a lab, so they didn't have to mine ammonium nitrate anymore. And that allowed them, even though they were blockaded, they could keep producing gunpowder. They couldn't keep producing food and things like that, so the average person starved, but at least they had plenty of bullets. But then on the flip side of that, when the war was over, like Max said, the ammonium nitrate is a really important component of fertilizer. Any soil that is deficient in nitrogen, you add ammonium nitrate to it. And so this has also led to an agricultural boom in a lot of areas where traditionally you couldn't grow crops, because you were able to make as much ammonium nitrate as you needed to get nitrogen into the soil and start producing more crops. So it led to an overall decrease in worldwide hunger. But also the same technology was used during World War I to cost millions of lives because it prolonged the war. It's really similar in a lot of ways to nuclear power, right? Nuclear power plants versus nuclear bombs. Same technology, same science being used to different ends. It's not that technology is inherently good or bad, it's how it's used. I see a hand over here?
Yeah, is that why if you buy too much fertilizer, you get on that?
Yep. So the anybody, you wouldn't remember it because I barely remember it. The Oklahoma City bombing in the 90s. Basically an entire federal, I think it was like 5 or 10 story building in Oklahoma City was completely destroyed because was it Ted Kaczynski? Or what? Timothy McVeigh, the other one. Ted Kaczynski is the Unabomber. Timothy McVeigh just drove a pickup truck full of ammonium nitrate fertilizer with a detonator in it into the parking garage of the federal building in Oklahoma City. And that was a big enough explosion that it demolished the whole building. So
And a daycare.
and a daycare, including the daycare that was on site as well. Clearly, technology can be used for good or bad, depending on your end. So anyway, with that historical context to this reaction, there's a reason why you always see this, and because it has a equilibrium constant that's not either massive or tiny. A lot of equilibrium constants wind up being like 10 to the 15 or 10 to the minus 14. They wind up either being huge or tiny. The Haber process has a equilibrium constant that's more reasonable, closer to 1. So if we measured equilibrium constants, or the equilibrium concentrations of nitrogen, hydrogen, and ammonia, we can calculate equilibrium constant, right? How do we write the equilibrium expression for this reaction? What would it be? Products over reactants. So NH3 don't forget the coefficient. To the 1 and hydrogen cubed. So if we actually want to get a numerical value here, all we do is we plug in the numbers. And then hit enter on our calculator, right? Just a little arithmetic. So K equals 0.72 molar squared over 0.10 molar times 0.20 molar cubed. Easy enough to plug that into your calculator, right? We get 648 ish. Make sure you can plug this into your calculator and get the right answer. Don't, use extra parentheses if you need to make sure. If you're getting, let's see, if you're getting a number that's significantly different, by which I mean off by a factor of 10, then you probably multiplied by instead of divided by. Landon? For these KC values, where we're talking about concentrations, it's always going to be molarity. When we start talking about gases, we'll find out that we can actually use pressures instead of concentrations because they wind up being proportional. But in that case, we're actually calculating KP instead of KC. So those are our 2 units. If it's KC, though, it's always going to be molarity. Now that you've learned concentrations, we basically aren't going to use units for concentrations besides molarity because that's chemists want everything in molarity because it's way easier to do calculations with. All right. Well, that doesn't seem too bad, right? Keep talking about how we're going to learn new tricks and how the math is tricky, though. What happens when we know the equilibrium constant? First off, I guess, how many sig figs do we get to keep here? Just 2, right? So 6.5 times 10 to the 2. And we usually don't write units on the equilibrium constant itself because you're going to either wind up with all your molarities canceling out and not having any molarity, or if you have a different number of molecules on top than bottom, then you're going to get, like in this case, we'd get 1 over molarity squared for our units. That's not a real unit. That doesn't mean anything. It's basically just there because of our relative concentrations. If you really want to track it, the units, and see what's going on with that, it actually has to do with probabilities that things run into each other, and you actually have to do a bunch of substitutions. So the units do have meaning to some extent. We're not going to do anything with that in this class, though. So all of our equilibrium constants are going to be unitless. And we're okay with that for once. Because really it's a ratio, right? And lots of our ratios didn't have any units. They were just ratios. In this case, it's ratio of products over reactants. All right, so if we have this reaction, let's say we have a set amount of nitrogen and hydrogen, and we want to know how much ammonia we can make. Well, the tricky part here is that solving for the amount of ammonia takes a little bit of substitution, right? Because we can just say the amount of ammonia at the end is X, but then how do we know what we're plugging in for these? because everything's changing at the same time, right? So, because let's say we started with those initial concentrations, so 0.10 moles per liter nitrogen, 0.20 moles per liter hydrogen. And we are trying to figure out how much ammonia we can make. Well, we know that it's going to stop when it gets to the right ratio, but all of these numbers are changing at the same time, right? Every time you make 2 moles of ammonia, you're losing 3 moles of hydrogen and 1 mole of nitrogen. So really, we have one big system of equations here where everything's changing. But because the reaction's balanced, we know that they're all changing close to this, or with a related amount. Right, so what we're going to do to figure this out, what the equilibrium concentration of ammonia is going to be, is we're going to use a tool called an ICE table. An ICE table, ICE stands for initial, change, and end, or in this case, equilibrium. So our initial conditions are 0.1 moles per liter of nitrogen and 0.2 moles per liter hydrogen. What is our initial amount of ammonia? If you're not given a number for it, we can assume it's 0. How much are they all going to change? Well, let's say that the nitrogen, are we gonna be gaining or losing nitrogen? We're using it up, right? It's a reactant. So we could just say minus, and we don't know how much it's changing. So what do we do in math when we have an amount that's, we don't know what it is yet? X. Let's think about hydrogen. Hydrogen's being used up as well, right? So it's minus. What could we plug in there?
3x.
Why? But because we know it's not the same as nitrogen, but we know it's changing in a related amount. So Y is 3x. Because we know that every time it uses 1 molecule of nitrogen, it's using 3 molecules of hydrogen. Right? This is basically just stoichiometry written in a table form instead of writing it out as conversions. How much is the amount of nitrogen going to change then? Is it going to be a plus or a minus? Plus, we could write Z if we wanted to, except it's more advantageous to keep everything in the same variable, right? So how much ammonia are we making? 2x. The last row of this table, the equilibrium row, you just add up the rows above it, or the columns above it. We started with 0.10 moles per liter of nitrogen, and we're using up X. So at equilibrium, we're going to have 0.10 minus X. Seems easy enough, right? What are we going to get for hydrogen then? 0.2 minus 3x. And for ammonia, 0 plus 0x, or just 2x. Now we have something we can actually solve for x. How are we going to solve for x? Say it again. Factoring. It's both simpler and more complicated than that. We're going to plug it in here. We already have an equilibrium expression, right? We know that what K is. We have a value for K. If we plug in all of these values in here, we can solve for X. And it gets too tricky for factoring. If it was a simple quadratic, then in theory, we could set it equal to 0, use a quadratic equation, factor it to figure out what x is. It's going to be way nastier than that, though. Because what do we get when we start plugging stuff in? We're going to get, here's our products, right? So 2x squared, because concentration of ammonia squared, over concentration of nitrogen, 0.10 minus x, and 0.2 minus 3x. To the third. It's still just one equation with one unknown, right? But it's a particularly nasty one when we start simplifying this all out and trying to solve for x. Basically, we're going to get something you can't solve for by hand. Everybody knows the quadratic formula, right? Quadratic equation. Does it work? All over 2a. Does anybody know the x to the third version of that? It's worth looking at just how ridiculous it is. The cubic I saw it in there in the thumbnail. This is why nobody likes Google. There it is. Now it's already done the substituting, so I don't want that. Basically, the point I'm trying to make is it's a ridiculously complex equation. And the problem with it is even if we did want to find the exact answer, it's not going to work because there's some chemical equations where we have a value that's to the fifth, right? Where we have a coefficient of 5 on some of our balanced reactions. Turns out there's a mathematical proof that you can't have a quadratic equation for powers of x greater than 4. It's been mathematically proven those equations don't exist. Not just that they're too complicated. There is no one equation to solve for all of those if you get past x to the 4th. X to the 3rd you can solve with the cubic equation. X to the 4th you can solve with an even more longer complicated equation. X to the 5th has no analytical value. So how do we solve that then? How do we solve this if we don't want to have to deal with the cubic equation? You graph it. You can use a calculator. The other way of looking at it is you just use a solver. You use Wolfram Alpha. It both plots it so you can see it, and it'll also solve it for you. We talked about Wolfram Alpha in this class? Okay. This is where it really shines. Quadratics that you don't want to deal with by hand. So, and we just type it in. I'm even going to keep extra sig fig just for the sake of. Is this not? There we go. Equals 2 times x to the 2 over parentheses 0.1 minus x times 0.2 minus 3x to the 3rd. Solve for x. No, did I mess something up? Yeah, I just rewrote it. So we get a complicated function. I don't want to say complex because that means something different in math. What does complex mean in math? Anybody know? A complex number in math means it involves both real numbers and imaginary numbers. We don't want to deal with I.
It's like 2.
Yeah, so get away. We don't want to deal with that, so I'm just not going to say. And that's actually what it shows you answers. So when you learned the quadratic equation, you were taught, oh, sometimes you get an answer that doesn't exist if you get square root of a negative, right? Well, really, that's just a complex answer. It's not a non-existent answer. It exists outside of the real plane, is the way that mathematicians would phrase it. Here's our 2 real answers. It solved it for us. That's wonderful, isn't it? We didn't have to do all that nasty algebra by ourselves. We just had to set up the equation and hit a solver. That's a totally valid way to solve these problems. How do you show your work on that? Use a solver. I'm going to teach you another trick to get around needing a solver, so that you don't. If you can use a solver. You can't use Wolfram Alpha, but if your calculator has a solver built into it and you know how to use it, then I use the solver as a valid answer on the final. If you don't, there's actually another way to solve some of these that we'll talk about in a second. So we got 2 answers though. They can't both be true, right? Which one's true? Is x 0.025 or is x 0.13? Why? Take one? You had a 50-50 shot. I like your odds, but no. Why can it not be 0.15? Who said that? Good job, Gabby. How do you know it's too big? It would give us a negative concentration. 0.1 minus 0.15 would give us a negative concentration for our nitrogen at equilibrium. That can't be true, right? We can't have a negative concentration. So a lot of these, where we wind up having to plug it into a solver, we're going to get more than one solution. Only one of them will make sense though. You'll never get a case where 2 of your answers are both plausible. If you get 2 or more answers, all but one of them are going to be impossible. Like x can't be a negative number, right? Not in this case, because again, we wind up with the same thing. If x was negative, we get a negative concentration for our product, and we can't have that. Right, so our x has to be 0.025. And if you want to check your work for that, just go back and plug 0.025 into this, and you should get 648 back out the other side. Right, so this tool, we see it used most frequently with equilibrium, but really anytime you've got a reaction happening and you care about more than one concentration at the same time, like in all of our theoretical yield excess reactant questions, we could actually use an ice table, right? Because you could do the same thing and then solve for x, and then then plug it in, and that gives you your excess reactant. It gives you your theoretical yield at the same time, right? This is basically just a way of doing stoichiometry for the whole system at once. And the key is using x for all of your changes and just using those coefficients in there. So just to bring it back to the historical note here, that's not very much product for how much reactant we put in, right? We wound up with a whole lot more reactant left over. So what Fritz Haber actually discovered was not actually this reaction. He actually figured out that you could take this ammonia gas, and if you cool it down enough, then the ammonia gas turns to liquid ammonia, which basically is a way it removes ammonia from the system, and you never let it reach equilibrium. You remove the product as it's being made, And so it'll keep making product because you never actually get to equilibrium. All right. I already mentioned this part. If K is much greater than 1, that means the top half of our ratio is much bigger than the bottom half of our ratio, right? And that means that at equilibrium, usually you're going to have more products and reactants. That's not exactly what we saw here because of those squared and cubed terms. We still wound up with a whole lot more. It's not a whole lot more. We still wound up with more reactant than product because of these higher powers. But this is just a way to visualize what's going on. Plus, K is not actually that big. For this one, 648 is not that large of a K value. By large K value, a lot of times we're talking about 10 to the 5 and larger. If K is really, really small, that means that you're going to favor reactants. It means the reaction doesn't really happen very much. All right, so let's do one of these problems without a solver. We'll do, and we're going to tie pH back to it too. Because everybody was hoping for more practice with pH too, right? So how did the titration lab go yesterday? Anybody run your numbers yet? Okay. Let's look at the reaction of acetic acid and water. Acetic acid wasn't on our list of strong acids, right? Which means now we define these terms. Anything that's not a strong acid is an equilibrium reaction. All of our strong acids, we could just assume the reaction goes to 100% to completion because equilibrium constant is so big. But in this case, for all of our weak acids, that's not true. So when you put acetic acid in water, you're going to get hydronium and what? What's our other product here? Say it again. Not quite. That was if it was water. Acetate. Good. I really appreciate that everybody in this room is willing to just throw stuff out there. That makes my life a lot easier when it's not just dead silence when I ask a question. So, right or wrong, I appreciate the participation. All right, so let's say we had a starting amount. If this is an equilibrium reaction, it has its own specific equilibrium expression, right? And equilibrium value. What's the equilibrium expression going to look like here? What's the first rule of equilibrium? Products over reactants. Good. So K is equal to what? H3O plus the acetate. Good. And what's in the denominator? The acetic acid
Plus 1. 4 times 1.
times water, except what's the third rule of equilibrium? Liquids and solids don't count. So because the water is a liquid, we're going to leave it off because its concentration is constant. And there's a value for this. At room temperature, there's actually, if you look at the back of most chemistry textbooks, especially Gen Chem textbooks, there's just tables of K values for common reactions. K for acetic acid and water is 1.8 times 10 to the minus 5. It's just the most common example that we use for weak acids and for equilibrium. So I happen to have that one memorized. If you don't have it memorized, I'll either have to give it to you or you'd have to look it up on a test. Obviously, I'm going to give it to you. I'm going to just say the equilibrium constant for this reactant is 1.8 times 10 to the minus 5. If we have a measured concentration of, let's say it's 0.15 moles per liter. That's stronger than vinegar, but it's reasonable concentration. What's the pH? What do we need to find? How do we get to pH? pH is what? Minus log of concentration of hydronium, right? Of H3O plus. Yeah. So if we solve this equilibrium problem, if we figure out how much hydronium there is at equilibrium, we can take the negative log of that and we'll get the pH. So how do we fill this ice table out? As normal, as one does. How much is our concentration of acetic acid going to change? Positive or negative? Are we going to be using this up as it reacts? Yeah, it's a reactant, right? The minus. Do we have a number we could plug in there or not? So just minus X. Do we care about water? It doesn't show up in our equilibrium expression, so it's not going to be important for us for solving for X. If we're assuming we're within sig figs, we're going to start with 0 hydronium and 0 acetate. So what does their change row look like for both of them? Plus X. For both of them, right? We're making both of these every time this reacts with water. So adding up the columns, we get 0.15 minus X for our acetic acid and X for hydronium and X for acetic acid. Sorry, acetate, thank you. Which means we can start plugging things in over here. I had to erase the expression to make room here. Is everybody okay if I erase the top half of the ice table now? Oh no. Did anybody watch any really old Saturday Night Live? Like from the 70s? Mr. Bill, ring a bell? I got one chuckles, that's a win. Whether that was because it's so far off base or what. Mr. Bill was a little claymation character. Oh no! The pan would come in. Like, oh no, Mr. Bill, here comes the refrigerator, and squish. It was so stupid. It was very 70s humor. It was still pretty funny, at least when I was in middle school. I wasn't in middle school in the 70s. Don't worry. If we're trying to plug things in here, it was concentration of hydronium and concentration of acetate. And then on bottom, it was C2H3O2. We have expressions for all of these now, right? Concentration of hydronium at equilibrium is X. Concentration of acetate at equilibrium is also X. So that's going to wind up being X squared on top. Our concentration equilibrium of acetic acid is 0.15 minus X. all of that equals 1.8 times 10 to the minus 5. That's a lot less scary looking than our other expression. That's still a quadratic, right? We still are going to wind up with x squared and an x here. You could use your solver at this point, get a value for x. The trick, if you don't have access to a solver, if k is really small, what do we know about x? If k is really small, what do we know about the ratio of products of a reactants? Which is bigger, products or reactants? Reactants is going to be much bigger, right? So if k is really small, what do we know about x? X is also going to be really small, right? If x is really small, our final concentration of acetic acid is going to be really close to our initial concentration of acetic acid, won't it? Like, let's plug a number in. Like, let's just say we solved for this and we got x was 0.001. If x is 0.001, what's your final concentration of acetic acid? Does it change? Not within sig figs, right? It's still going to be really, really close to what you started with, right? Effectively, the reaction's just skimming a little bit off the top. Nobody's ever going to notice. So here's the big step. And this is not a real math step, it's a math step for this class. Math step for this class, for solving this, is it's a reasonable step to say, assume x is close to 0. If x is really close to 0, then this number is going to be really close to 0.15, right? So basically, then you just rewrite this as x times x over 0.15 equals 1.8 times 10 to the minus 5. Now all of a sudden that's a lot easier to solve, isn't it? It's not a quadratic anymore. Basically, a big chunk of why we spend so much time talking about sig figs and uncertainty is so we know in science classes when it's acceptable to assume something is close enough to 0 that we can ignore it. And that's exactly what we do in this case. When k is really small, x is going to be really small. And if x is really small, this concentration isn't really changing. Right? The trick is we can't assume that all of our x's are 0, or else we're just going to get 0 over 0.15. And so we make any differences are going to go away. Did I see a hand? So we make an assumption, and now all of a sudden we can solve it. Now we're going to get x squared over 0.15 equals 1.8, 10 to the minus 5. X squared equals 0.15 times both sides, so 2.7 times 10 to the minus 5, 10 to the minus 6. Yeah. Square root of both sides. It's going to give us so the last step, if you're going to make this assumption, one, you have to write the words, assume x is close to 0. Don't just disappear the x without saying something about it. And then the other, anytime you make an assumption, you have to show that your assumption is valid. And the way we do that is as long as x is less than 5% of what we started with, then that's a valid assumption. So, and the way you show your work for that is you just take 0.05, 5%, times your X value. Or sorry, times your initial value. And as long as X is less than that, then our assumption is valid. You just have to write this basically and actually check it. So 5% of 0.15 is what? .0075. Is X less than that? Yeah. So as long as you write this and say X is less than that, you can say your assumption was valid. Last step. What was the original question? Who remembers? That was like 5 board sweeps ago. What's the concentration of H3O plus? Because what were we trying to get to? pH. Concentration of H3O plus is X. So we just that point. So which one? That was X squared. So we took the square root of both sides and got this. All right, so if we want to know the pH, we just solved for a hydronium concentration, so we just take the negative log of 0.0016, which should be something between 3 and 4. No, between 2 and 3.
2.795.
So does anybody have an issue with making this assumption? Usually somebody who's taken lots of math classes usually will say, I don't like making that assumption. I'd rather use the solver or use the quadratic formula. That's reasonable. Mathematicians don't like it when I do this either. But that's what makes them mathematicians and me in the real world. If we plug this in, if we didn't make that assumption and we plugged it into Wolfram alpha, we get 2 values. Oh, would you look at that? 0.0016. Within sig figs, if we're keeping track of our sig figs properly, you should get the same answer if that assumption is valid. If the assumption is not valid, you have to use a solver or you have to use a quadratic formula. Those are the ones I'm not going to give you that on a test. Landon? So if we go through this process and you find that X is more than 5% of what you started with, then we can't say our assumption was valid. So basically, this is our check to see if it was okay. And the cutoff usually winds up being around 10 to the minus 4. As long as X is smaller than 10 to the minus 4, it's going to be good. You still have to write the assumption and show it though. All right.
What do you do if your assumption wasn't valid?
Then you go back and you find a solver. So you did a little bit of algebra for nothing, but you were gambling that maybe this is going to save me some work. But again, as long as K is 10 to the minus 4 or smaller, it's almost always a good assumption. And if K is bigger than that, then you might have to find a solver. But I'm not going to give you any. So on the test, on the in-class final, I will not give you any where the assumption is not valid. I'm only going to give you ones where you can make that assumption it'll be valid. So I still want you to show this so that you're dotting your I's and crossing your T's. All right. All right. we'll do a little bit more practice with this and we'll talk about gases on Monday. I'm deciding. Do I have a quiz outstanding? I think we're okay without the quiz this week. Right? As long as everybody turns in at least one outstanding assignment if you have any. And I'll grade at least one assignment. Max, if you don't want to make that assumption on the test, just make sure you've got it calculated with the solver and learn to use it. And I don't have it. We probably have a need to borrow, but I actually never use the solvers not built into the PIs. So if I don't have a computer and I can't make that assumption, I'm SOL myself. So that's fine. You're just gonna have to make that assumption. Just trust and then check it. As long as your assumption's valid, then you're just being a scientist instead of a mathematician.